anniversary videos. She's not going to film the audience, so don't worry about it. If it does, it'll be incidental. It'll just be the back of your head or anything. So nothing that is any commercial or anything that will be done with this, okay? All right, everything cool? And let's begin. Good evening, ladies and gentlemen, and welcome to the Hubble. You want to say good evening? Good evening, ladies and gentlemen. Thank you. Welcome to the Hubble Space Telescope Public Lecture Series here at the Space Telescope Science Institute. I'm your host, Dr. Frank Summers of the Office of Public Outreach. And as usual, if you came in and went over to our table, you get an image. Tonight's image is the 25th anniversary kickoff year image of the pillars in the Eagle Nebula. You get 2 for 1 tonight. You get both the visible light image and the infrared image. This was released in January, and I hope you were here earlier in the year when I discussed the weirdest stars in the universe. Doesn't that sound like an intriguing title? All right, Emily Levesque from the University of Colorado. Now, most of the time our speakers are from here at Space Telescope because we don't have a budget to import speakers. So she unfortunately was visiting the Space Telescope Science Institute, so we were able to get her to give a talk tonight. Let's see, our website for finding out about information about the talks. If you go to hubblesite.org, go talks, or simply search Hubble Public Lectures, you will find us, the list of the upcoming lectures, information about the lectures, the information about the observatory, and also, very important, this archive, which goes back 10 years now. 10 years of this public lecture series has been archived by our wonderful webcasting team, and you can go back and find a lot of really, really cool lectures. Let's see, email. We have, as I announced last month, I believe, or the month before, we have a new procedure for getting yourself on the email list. You can go to maillist.stsci.edu. You will see the public lecture announce email list there, and you can sign up for it on that website. Or you can just provide your email address to me, and I will add you to it. A way to do that is to send email to publiclecture@stsci.edu. You can also send comments or questions to that email address. For those of you who like to do social media, Hubble has a variety of social media interfaces. We're on Facebook. We have 2, not 1, but 2 Twitter feeds that you can follow. We're on Google+, which we must be one of Google's favorites because we've got several million followers on Google+, which is about 10 times as many as we have on Facebook. So Google must be promoting us there. We're also on Pinterest, which is honestly something I've never been on. So if you know what that is, you probably know a lot more than me. Myself, I'm on Facebook and Google Plus and Twitter, and I do that every now and then. I'm rather sporadic with it because I got lots of other things to do, unfortunately. Also, unfortunately, there will be no observatory after the talk tonight. The Maryland Space Grant Observatory, md.spacegrant.org, is where you can find information about it. They sent me the email saying, hey, it's going to be cloudy and rainy tonight, and it was cloudy and rainy when I came in, at least. So we won't have observing, but they do have observing most Friday nights. So check their website and get on over and see what you can see from here in downtown Baltimore. Not as good as if you get way out away from the city, but they still have a wonderful facility across there. All right, and I'm going to give you a short news from the universe for June 2015. I have to say I was caught up with some emergency projects yesterday and today, so I don't have quite as many stories as I usually do, but I still have one really cool story for you. All right, and that story is a supernova with a split personality. This is so cool because we've never seen this before. All right, so first of all, you guys have seen gravitational lensing, right? How many of you have been here a lot and know my 3-word summary of general relativity? All right, in the back, right? Anybody remember it? All right, general relativity, the 3-word summary is mass warps space, okay? So what you are looking at here is the mass of this galaxy cluster warping space so much that the galaxies behind it have become distorted as they pass through this warped space. So these stretchy things here, gravitationally lensed arcs, are galaxies behind the cluster whose light has been distorted while passing through the warp space of the cluster. All right? And we describe it like this, in that here's the light of a distant galaxy, here is the huge mass of this galaxy cluster, and the light is redirected by the mass of this cluster, and so that the cluster acts like a lens. We call this gravitational lensing. All right? And this cluster is just one form of gravitational lensing, by cluster gravitational lensing. We can also have individual galaxy gravitational lensing. So this is one individual galaxy here. This thing in the center here is just one individual galaxy. And to the left and to the right and under the center of this galaxy, giving you 4 images of that same object. Kind of cool, right? Now, the third thing that you've heard of, that you may have heard of before, especially the regulars have also heard of, is that new project that Hubble has been doing for the last couple of years called the Frontier Fields. Now, the Frontier Fields is taking 6 big clusters of galaxies and using those gravitational lenses to look deeper into the universe, because the light from the galaxies is not just distorted, it's also amplified. So by using Hubble's lenses, as well as this cluster lens, we can see just a bit further into the universe than Hubble otherwise could. And that's what's happening with the Frontier Fields. Now, the observations for the Frontier Fields are being timed such that if there is a supernova appearing in any of these, we can catch the brightening of the supernova. So that if you take the images at specific intervals and then subtract the 2 images and there's a bright spot in it, you may be able to catch supernovae. All right, especially very distant supernovae, which are the ones that are really valuable for understanding cosmology. So they found one in this cluster here, max J1149.5 plus 2223. Yes, I know it well, good friend of mine. Okay, so actually, by the way, it was interesting because in that thing it was called 1149.5, and this one's 1149.6. These are actually just the right ascension and declination from them, but different groups actually have a slight difference in the point there. Okay, so this is the MAX cluster, okay? And this is one of the clusters they're studying for the Frontier Fields to see these distant objects as well as to see these supernovae. Well, they found a supernova here, and it's in this galaxy here. But this supernova has been gravitationally lensed by the galaxy. You've got 1, 2, 3, 4 images of the supernova. This is the left and to the right are of different distances, which means it takes different times for the light to come across and around it. So if we watch all 4 images, they will brighten and fade at different times. And using this, we get essentially 4 views of the same supernova explosion. How cool is that? But wait, there's more, because this is in a gravitationally lensing cluster, and it's not only lensed here, but it also has been lensed elsewhere in the cluster, okay? So you've got 4 images of the supernova here, plus you've got an image of the supernova that was believed to have been over here, which we believe, if it was there, would have been observed about 5 years ago. And then another one, oh, I'm sorry, the central one would have been about 5 years ago, and they predict that there would be another image over here that will be seen in a few years. All right, so using the mass map that they've gained from Frontier Fields, they're able to predict that not only does it come through here, but it also should have come through here and will come through here. So all of the observations they're getting today, this year, of the supernova, they can then second guess and check and see what happens in a few years when it comes through there. That's really cool. So this is a supernova with a really split personality. It's a combination of supernova and a huge galaxy cluster and gravitational lensing, giving us a view that we have never had before. That's kind of cool. All right, a short update for our second story tonight. That Ceres is really ready for its close-up. Okay, now you may remember that the Dawn mission went into orbit around Ceres starting in March. And it didn't, if you were here that month, I showed you it didn't actually go into orbit. It sort of slowed down and then starts and then moved into its observation orbit. Well, it's now gone through its observation orbit and it's getting much more detailed images. So this is the kind of image that we were getting pre the observation orbit, and this is the kind of image we're getting now. And so let me go here and show you. That's the kind of detail we're now seeing about Ceres. Ceres is the largest object in the asteroid belt. It is officially categorized as a dwarf planet, all right, because it's large and spherical, but it is, to most astronomers, the largest asteroid. All right, and you can see the kind of detail we're getting on it. We're going to map Ceres in great detail. The Dawn mission will stay with Ceres for another year, okay, till early 2016. It will continue to do these mapping and measuring the characteristics of Ceres. And the exciting thing for you guys, I have secured Lucy McFadden from Goddard Space Flight Center to come and give a talk in December of this year on the Dawn mission. She is one of the world experts on the Dawn mission and asteroids and objects like this. And December, she'll be here to tell you all sorts of details that we're just now assembling. All right? Okay, so now we move on to our featured speaker. Our featured speaker tonight is Dr. Emily Levesque. She's at the University of Colorado, and she is a Hubble Fellow there. What does that mean? Well, one of the great programs that came along with the Hubble Space Telescope was the support of young astronomers who had just finished their PhDs, to give them money to work on Hubble Space Telescope related projects for several years. And these are some of the most prestigious fellowships anywhere in astronomy. So when I say that she's a Hubble Fellow, you should recognize that she's good, okay? All right? You have to be really good to win a Hubble Fellowship. All right, and so Emily is at the University of Colorado doing her Hubble. One of the cool things about the Hubble Fellowships is that you can actually take them where you want. You can say, you apply for a Hubble Fellowship, and you say, I want to do it at this university. And all you have to do is get somebody at that university to sponsor you and say, yes, we'll accept them if they take a Hubble Fellowship. So you not only get money, but you also get your choice of where you want to do your research, which is makes these really, really cool. Previously to that, she was at the Institute for Astronomy in the University of Hawaii doing her graduate work, and she did her undergraduate work at MIT. So if you aren't impressed by that, you just don't know what you're talking about. Ladies and gentlemen, Dr. Emily Levesque.
So first of all, I want to make sure that everyone can hear me. I realize that question is totally useless if the answer is no, but good to know. So I'll be talking to you tonight about the weirdest stars in the universe. Somebody coming in asked me what the criteria is for calling a star weird. How do you establish that something is unarguably weird? And you could really make the argument that many, many stars in our universe are weird in some way. I'm trying to go for the very strangest and most bizarre stars of them all. And I think to start off and to sort of establish what we mean by weird, it's helpful to talk about what we would call a normal or garden variety star. So this diagram that I'm showing is a very common diagram used by professional astronomers. It's called the Hertzsprung-Russell diagram, and it gives us a quick and easy way of describing almost any star that we observe in the universe. We plot temperature on the horizontal axis. To the left is very hot and to the right is very cold. And on the vertical axis, we plot luminosity, or basically how bright the star is. So if you know a star's temperature and if you know a star's brightness, you can figure out where it lands somewhere on this diagram. So we can take our sun, which has a temperature of about 5,800 Kelvin, and it has a brightness of about 1 solar luminosity. Surprise, it's the sun. And we can drop it right here. So you'll notice our sun is sitting in kind of a crowded place, and it's sitting with a bunch of other stars on this diagonal line that runs straight through the middle of the plot. This is what we refer to as the main sequence for stars. When stars are born and when they start burning hydrogen, and while they spend a good portion of their lifetime burning hydrogen, they all land somewhere along this main sequence. So a main sequence star is something that you can think of as maybe a pretty normal star. And a smallish star like our sun would also be considered fairly normal. What I'm going to talk about tonight are stars that live up here at the top of the Hertzsprung-Russell diagram. These are stars that are much more massive than our sun. They are at least 8 times the mass of our own sun. And something that's going to be a little bit of a theme tonight that you'll notice is that astronomers are pretty literal when it comes to giving things names. So we call these massive stars. They're much more massive than the sun. There we go. I always like to try and point out some good examples of massive stars that you can find when you're stargazing on a beautifully clear night like tonight, but maybe sometime soon when you can actually see the sky, we can talk about some examples of massive stars that you can find. When a massive star begins its life and lands on that main sequence and is burning hydrogen, we call it a blue supergiant. And a great example of one of these is Spica in the constellation Virgo. Now, Spica is much, much hotter than our sun. It has a surface temperature of about 22,000 Kelvin. Remember, our sun was about 5,800. It's much hotter than the sun. It's about 7 times the physical size of the sun, and it was 10 times as massive when it was born. So Spica is a great example of a blue supergiant. Another example of a star that's a little further along is one of the stars that you'll see making up the summer, and it's about 200 times the sun's size right now. So stars will hang out over on the blue hot side of the HR diagram for quite a long time. They'll sit there burning hydrogen. But eventually the stars run out of hydrogen and switch over to burning helium. When this happens, they very rapidly run across the Hertzsprung-Russell diagram as they cool off and as they start to expand. Stars actually spend a really short period of time in this little yellow region of the diagram. We actually call that the yellow gap because stars only spend about 100,000 years as yellow supergiants. It sounds like a long time, but when stars live millions and millions of years, it's really just a blink. Yellow supergiants are kind of rare because they don't last very long. You have to be catching them at exactly the right time. So something I find kind of amazing is that Polaris, our North Star, is actually a great example of a yellow supergiant. This is almost exactly the same temperature as our sun, but it started out with 8 times the sun's mass, and it's about 46 times the physical size of the sun. So it's a great example of this really fleeting stage in stellar evolution. Then finally, once a massive star has finished this trip across the Hertzsprung-Russell diagram, it will end up as what we call a red supergiant. And we have another great example of one of these in the night sky right now. In the constellation Scorpius, which you can find if you look for these 2 next close to each other stars in the Scorpion's tail and then follow the curve around, you'll see a great example of a red star named Antares. So Antares is much colder than our sun. Its surface is about 3,400 Kelvin, but it was 13 times the mass of the sun when it was born. And here's the impressive thing about Antares, it is 700 times the physical size of our sun. To try and put that into context, this is a little PowerPoint drawing of what Antares looks like, and that's the planet orbits in our solar system. If you dropped Antares where our sun is, it would reach out past the orbit of Mars. So this sounds tremendous. This sounds very large and like it would justifiably be called a very weird star. But as it turns out, we've found stars that are much, much physically bigger than this. And to explain why, I want to talk a little bit about how we study how stars evolve and a kind of interesting puzzle that we had to answer about red supergiants. So I described how massive stars evolve, talking about how they start on the blue, burning hydrogen, they switch to burning helium, they scoot across the HR diagram, and they wind up as red supergiants. We can actually trace out this journey that the stars take. We can say, okay, say a star that's 15 times the mass of our sun will start out here, cross the HR diagram, and wind up here. We call that trace the star's evolutionary track. It's a shorthand way of looking at how that star is going to appear over the course of its life. Astronomers will actually simulate entire collections of evolutionary tracks. We'll make our own, much less pretty, but very useful, version of the Hertzsprung-Russell diagram made up solely of these tracks, looking at how a 12 solar mass star will behave and how that's different from what a 40 solar mass star will do. And we can use this to summarize how stars should look at every point in their lifetimes. These are all generated by computer models. So a good way to test a computer model is to drop a bunch of models on a diagram and then grab actual observations of stars and see if the two match up. So about 15 years ago, people started doing this for red supergiants and dropping red supergiants that had actually been observed on the Hertzsprung-Russell diagram. So it's not quite right. You can see that the red supergiants don't quite land where we want them to land. They're just a scotch too far to the right. Remember, the x-axis goes from hot on the left to cold on the right. So these red supergiants look too cold. They're landing in this region of the diagram to the right of the evolutionary tracks. And in this region, stars are not supposed to be able to exist. They're not supposed to be able to stay stable. The star should immediately be trying to leave and get back to the right side of the tracks. So this was a kind of odd and surprising result, and we weren't quite sure what the problem was. And one explanation that came up was the idea that maybe the temperatures we were assigning to these red supergiants were wrong. So to talk about how we actually figure out a star supergiant's temperature, we need to look at a spectrum of a red supergiant. So this is a typical red supergiant spectrum. When we talk about a spectrum, what we're doing is taking all the light that we get from the star, breaking it up into little individual colors, and sorting the colors out. So we put the bluest light over here, the reddest light over here, and again, we have brightness on the vertical axis. So you can see it's a red star, so we're getting way more light on the red side than on the blue side. You also see all these kind of bites and all these bumps and dips taken out of the spectrum. Where those dips come from are from molecules in the atmosphere of the star. A red supergiant is so cold that it can actually build up huge amounts of titanium oxide molecules in its atmosphere. We don't get these in our sun. Our sun is so hot that it would immediately break a titanium oxide molecule up into titanium and oxygen just hanging out separately. In a red supergiant, we can make these, and they absorb light at very specific colors, which is why we get these dips. So as it turns out, the amount of titanium oxide in a supergiant atmosphere is directly related to how cold the supergiant is. So this is a red supergiant spectrum with the surface that's 4,000 Kelvin. For a red supergiant, that's pretty hot, although it's still way colder than our sun. If we cool this star off, we can watch what happens to the spectrum. And you can see that those bites out of the spectrum get bigger and bigger as the star cools off. We're able to make more and more titanium oxide, and it absorbs more and more light. So by the time we've gotten down to a really cold temperature, these big bands are enormous. What we realized that we could do is take spectra like this of a bunch of red supergiants and use the strengths of those bands to measure the star's temperatures. This was actually the very first research project that I did while I was an undergraduate student. I spent a summer at Lowell Observatory in Flagstaff, Arizona. I was working with Dr. Philip Massey on this project to redetermine temperatures for red supergiants. So the very first part of my project was going to Kitt Peak National Observatory down in southern Arizona. They actually let me open the dome of the 2-meter telescope. So this is me at 19. You can't tell, but I'm freaking out because they're letting me operate a 2-meter telescope. And I got to enjoy wonderful beginner's luck and have 5 perfect, clear, cloudless nights in a row on the telescope that let us get a bunch of spectra of red supergiants. We got all of the data, we analyzed all of the data, and we measured new temperatures for every single star. And then it was time to test what we'd actually done. So this, remember, was where red supergiants used to sit as compared to these computer models of how stars evolve. That was what they looked like before our project, and this was what they looked like when we were done. Yeah, so you can see that the agreement is now perfect. They sit exactly where we want them to, and this was a super satisfying result. This is a great thing to do if it's your very first research project. And we got really excited, and we started to write the paper to publish what we'd found. So we knew the temperatures of the stars, and we knew their luminosities. And there's a really common equation that you see used in astronomy. This is an equation relating the luminosity of a star to its temperature and its size. And from the research we were doing, we had almost all of this information already. We knew the luminosity of the star. We know what 4 and pi are because they're constants. Sigma is actually another constant, the Stefan Boltzmann constant, so we knew values for all of those. And we had measured the star's temperature, so the only thing that was left was to figure out the star's radius. We didn't know it right away, but we do a couple algebra rearrangements of the equation, and we can measure radius. Ta-da! So we sort of measured this as a matter of routine. We figured, well, we can, so we might as well. We'll put it in the paper, that'll be neat. And we started making a list of all of our stars, all of their temperatures, and all of their sizes. That's the number of times bigger the star is than the sun. And we were totally not paying attention to this column at all. We thought this was the really cool part. And it finally took one of our collaborators to email us and say, I don't know if you've looked at these radii, but some of these numbers are pretty impressive. And as it turned out, we had, by accident, discovered 3 of the largest stars that anybody knew about in the known universe. I showed you this graphic before of how Antares compared to the orbits of the planets in our solar system. Antares reached out to a little bit past Mars. This was the biggest star that we found. It reaches most of the way to the orbit of Saturn if we put it where our sun is. So I think that undeniably makes KY Cygni, not a terribly catchy name, but pretty good, a pretty weird and unique star. So I've been talking about red supergiants in this big puffed up stage near the end of a star's lifetime, but as we already heard about earlier tonight, I'm pretty sure you all know what happens after something is a red supergiant. It explodes. This is the point where we stop talking about stars and start talking about core collapse supernovae. So once a star has reached the end of its life, we see it create this amazing fireworks show that we see as a supernova. And it's good to talk about exactly how supernovae work and how something like this happens. So the image that I have up now is a cross-section of a massive star, and you can see that it's made up of layers of different elements. It looks like an onion that you cut in half. What happens is that a star will start out burning hydrogen in its core. It'll be burning hydrogen. This will exert a sort of outward push that counteracts the inward push of the star's gravity. So it helps the star hang on to this sort of delicate balance between gravity pushing in and the energy from burning hydrogen pushing out. Now, eventually the star, while burning hydrogen, will make helium. Eventually it'll go, well, hey, I'm out of hydrogen, but there's all this helium around, awesome, and start burning helium instead. And the star will go through burning progressively heavier and heavier elements for shorter and shorter periods of time. It will burn helium, it will burn carbon. Stars will spend about 3 days at the very ends of their lives burning silicon, and everything is going great, and that balancing act is being maintained up until the star tries to burn iron. So burning helium or hydrogen or carbon or any of those elements produces energy. But to burn iron, you need to take energy. So we're no longer pushing out against gravity, and at this point, that whole balancing act fails, and the star collapses inward on itself. We actually have an animation of how this works. So at this point, we are peering into the center of a massive star as it begins burning helium. Now, as it goes along, you'll watch the colors in the video change as it shifts to burning carbon or neon or oxygen, you'll see that brief period of it burning silicon, and then when it tries to burn iron, the balancing act of the star fails and the star collapses. You see a quick collapse followed by this amazing rebound that we see here on Earth as the fireworks show of a core collapse supernova. It's fun to see an animation of one of these, but it's actually just as cool to see what one actually might look like. This is a cave painting from Chaco Canyon in New Mexico. And what we think the painting is showing is a daytime moon shown here and this thing just to the left. We think that that is a depiction of a supernova that happened in the year 1054. This supernova got so bright that it was visible during the daytime for 2 weeks. You would have seen it in the sky sitting right next to the sun. It's definitely something worth painting on a cave about. So we think we have a record of it from New Mexico. Chinese astronomers have records of it. They referred to it as a guest star because it appeared for a while and then it left. It was recorded by Japanese astronomers, by astronomers in Iraq. And today we know exactly what this was. This was supernova 1054 that left behind what we know now as the Crab Nebula. It's one of the famous, beautiful images from the Hubble Space Telescope. So this was a very nearby event to Earth. This was a star exploding in our own galaxy, about 6,500 light years away. This was a great fireworks show. We would have seen it, like I said, during the day for 2 weeks. Most supernovae aren't quite this dramatic, and you saw some images of what supernovae look like a little earlier tonight, but I have another example for you here. These are some beautiful amateur photographs of M51. The first one is from January of 2005. And I'm going to flip to an image from July of 2005. You'll notice that the image will get a little bit brighter, and you'll see something else change as well. Did anybody see it? Let me see what changed. I'll do it again. Yeah, see the little boop that appears just about 6 o'clock under the center of the galaxy? That's a supernova. That's an enormous explosion of a star that's many, many times the mass of our sun. We see it as this little bing that shows up in a distant galaxy. That's supernova 2005 CS. What's even cooler is we have another image of this galaxy from June of 2011, and we got another supernova over here. 2005 CS is gone, it's faded away, but we now have supernova 2011 DH. So again, astronomers were pretty boring and practical a lot of the times when it comes to giving things names. When we name a supernova, we name it based on the year that we saw it and how many supernovae there have been in the year. So the first supernova of 2011 would have been 2011A, and then B, and then so on. And then when you get down to 2011Z, you just go back and start adding more letters. So you wind up with 2011AA, and so on. So if I'm getting it right, this was the 112th supernova that we had seen in the year 2011. I can see somebody counting, trying to figure out how many letters we can get through. We have actually now busted through this naming convention because we are finding so many supernovae every year. There are different surveys with different names that will use their survey name plus the year and letters to keep track of how many supernovae we're finding. So this is a nice method of finding supernovae. You monitor a galaxy and you wait for something to change, and you wait for this little bing, turn on brightness that we think represents an entire star dramatically exploding. Usually this works pretty well. This is a galaxy about 23 million light years away, so this is still a pretty good view. Sometimes, though, this can cause problems as a test for finding supernovae. The little dramatic-looking fuzzball in the middle of this image is the galaxy NGC 7649. The names get less interesting as we go further away. This galaxy is about 78 million light years away, and in 2009, we saw this happen. We saw what looked like a supernova appeared. We saw a star that got way, way brighter. I said, all right, it's 2009. It's the 250th supernova of 2009, so we'll name it Supernova 2009 IP. We will write it down in the record books. This thing has that name forever because it is definitely a supernova. And like most supernovae, we kept watching it, and it faded away, and then this happened. Came back. Yeah. Oops. So this star was not a supernova. We could monitor that place in the sky and measure how fast the material from that apparent supernova was moving, how fast the exploded material was moving away from the star. It turned out it wasn't moving nearly fast enough to be the true sign of an exploding star. This instead was something that we call a luminous blue variable. So again with the names. But one of these stars is pretty much exactly how you describe it. They're very luminous. For most of their lifetimes, they're blue. And they're very, very variable. What we think is that these are stars much, much more massive than our sun, 40, 50, 60 times the mass of our sun, that are nearing the ends of their lives and going through an unstable period in their evolution. They periodically erupt and throw off huge amounts of mass, sometimes over and over again. And we really still don't quite know why. We think that it might maybe be an attempt for the star to remain in equilibrium, we're not sure. But when a star does that, it will brighten and then dim again and resemble a supernova. Some people actually call these imposter supernovae. We have an awesome example of one right in our own Milky Way. This is the star system. There are actually 2 stars in there named Eta Carina. It's about 7,800 light years away. And this is a star that last underwent one of those big eruptions back in the mid-1850s. We have records of it. There are Aboriginal oral traditions that talk about this star. It became the second brightest star in the night sky for about, I think it was 1837 to 1854. And you can see exactly what's going on. There's a star in there somewhere, but most of what we see is all the material that was flung off of the star when it underwent this eruption. So the star is back to being relatively quiet now, but it's one of the most studied massive stars that we have because we are so curious about why it erupted, when it could erupt again, what we can learn from the material, what we can learn from the star there in the middle. It's a fascinating example. So going back to 2009 IP, this poor star that's forever now stuck with the supernova name, we observed it in 2009 and kept observing it. We saw it brighten again in 2010 and again in 2011. In 2012, we actually saw it produce what would have been the most dramatic eruption yet. It got way, way brighter. We measured the speed of the material that was flung off, and it was incredibly fast. And we think that it might have actually exploded in 2012. But we're not sure. So, I mean, you would think that a star that's like 50 times the mass of the sun exploding in a fiery death would be a pretty obvious thing to, did it happen or did it not happen? And it's really not, because all we get is the little blip from the star. This is one of the most interesting questions in supernova astronomy right now, and there are active campaigns to try and search this galaxy and see if the star really has disappeared or if it's just sitting there very dim, waiting to maybe erupt again someday. So those all count as weird stars, stars that pretend to be supernovae but aren't. And we've talked a lot about how supernovae actually happen, so now we can move on to what happens after a star goes supernova. I showed you this before. This is the Crab Nebula, the supernova remnant from the star that exploded in the year 1054. And you get all these beautiful colors from the Hubble Space Telescope, but there's one other piece of the remnant that you can't see in this image. Somewhere in the center of that remnant is something called a neutron star. Neutron stars are the leftover husk of a massive star after they have gone supernova, undergone core collapse, flung off this material. This is what is left of the star itself. Neutron stars are incredibly small. I was talking about stars that, cover the orbit of Mars or cover most of the way out to the orbit of Saturn. A neutron star is about the size of the city of Baltimore. They're tiny. They're also unbelievably dense. If you were to take a teaspoon of a neutron star, that teaspoon of material would weigh more than Mount Everest. And it's this extreme nature of the star that actually lets it work. Neutron stars are made, like the name suggests, entirely of neutrons. The reason that these stars even work are actually thanks to a principle of quantum physics. It's called the Pauli exclusion principle, and it's a rule that basically says that two neutrons, for example, that are in the same quantum state, two neutron stars that are just like each other, do not like being too close together. They can't occupy the same space if they're in exactly the same quantum state. So what it really means is that the star was collapsing and getting denser and denser and tighter, all of these neutrons were getting squeezed very close to one another, and they eventually started acting like you do on a crowded train. They started going, no, we hate this. We don't like being close to one another. This is terrible. And pushing back against that inward squeeze of gravity. This is called neutron degeneracy pressure, and it's so powerful that it's actually able to support the star. So it's a whole star supported by quantum physics instead of hydrogen burning or helium burning or any of the things that we see in stars while they're still alive. We had predicted neutron stars for a long time. They were predicted back in the early 1900s, but we didn't know for sure that they existed until we detected a specific type of neutron star called a pulsar. So pulsars are rapidly rotating neutron stars with very strong magnetic fields. We know that Earth has magnetic fields and magnetic poles. That's how our compasses work. Neutron stars and pulsars do too. What they do is they actually emit a beam of electromagnetic radiation along their magnetic poles. So they're emitting beams at one end and the other, and they're spinning very, very fast. So this makes them look like they're flashing or pulsing. This is how we named them pulsars. A good comparison for how this actually works, people will use lighthouses periodically, but with the advent of GPS, lighthouses are becoming less popular. I like using the example of an emergency light on top of, say, a fire truck. If you look at these lights closely, a lot of them will be two bright lights beamed out to either side on something that makes them rotate. So when you spin the two beams of light, the effect that you get is flashing. So the next time you see a fire truck or something with its emergency lights on, first pull over if you're in a car, and then think about how that is basically exactly what's happening in a pulsar. So a pulsar is actually spinning faster than this, usually. Something that is the size of the city of Baltimore will be rotating tens or hundreds of times every second. But it means that they give off a very specific observational signature that we can detect. And it means that we now have evidence that neutron stars actually exist. There's a star like this in the center of the Crab Nebula, and it's this little piece of star that's left over after a massive star has died. So they definitely count as weird stars. So I talked about neutron degeneracy pressure and how it can support a neutron star up to a certain point. Once a star gets too massive, or once a neutron star gets too massive, it will collapse into something that's infinitely small and infinitely dense. We heard the primer on general relativity earlier tonight. Mass bends space. So if you have an infinite amount of mass in an infinitely tiny space, that is how we get a black hole. It bends space-time so much that we get a region with incredibly strong gravitational influence. Not even light can escape from it, hence the name black hole. The problem with this is that it makes illustrations or images of black holes, it doesn't really work for a public talk because there's nothing really there. So what we can take advantage of is something like this idea of gravitational lensing that we talked about. We can't see a black hole itself, but we can see what it does to the objects and the light around it, and we can get some help from Hollywood, we can go into the realm of artists' renditions, and now we have an amazing black hole thanks to the movie Interstellar. So there's many different, there's one person that was like, yeah. So there's many different ways to make black holes. We have supermassive black holes that form at the centers of galaxies. We can make a black hole when we just pile too much mass onto a neutron star. Or we can make them when a very massive star, 20, 25, 30 times the mass of our sun, undergoes core collapse. That core will collapse straight, we think, into a black hole. What makes some of these weird, even by the standards set by black holes, which are all pretty weird to begin with, is that sometimes when a massive star collapses to form a black hole, we get something else happening as well. We get a bright and brief flash of gamma rays that we know as a gamma ray burst. We still don't understand exactly why gamma ray bursts happen, but we have a pretty good guess, and I have an animation of what that guess is. So this is another example of a massive star that's about to die. This is 30 or 40 times the mass of our sun, and this star is also rotating very rapidly. When that star collapses, it will make a rotating black hole in the center of itself. That black hole will start devouring the star from the inside. As that material is being pulled into the black hole, it ignites these jets that you see coming out either side of the star. Those jets are moving so fast that they emit gamma ray radiation. Eventually, the entire star has been blown apart, and this whole thing ends with that same explosive supernova that we saw from a normal star collapsing and dying and making, say, a neutron star. We actually found these in a kind of interesting way. First of all, I want to show that video again and point something out. This is a star that's 40 times the mass of our sun. This is an animation of the star dying, but this animation is happening roughly in real time. Gamma ray bursts last maybe 2 seconds to several hundred seconds. This one is maybe 30 seconds. That's how long it takes for this entire star to get consumed by the black hole that it has made and then detonate. So yeah, gamma ray bursts do not last long. It makes them kind of hard to study. And how we originally discovered them is actually kind of funny. This is an illustration of the Vela satellites that were launched into orbit in 1967 following the signing of the Nuclear Test Ban Treaty. So the job of these satellites was to sit and monitor the planet and look for a flash of gamma rays that would indicate that somebody was violating the treaty and performing a nuclear test. And the satellites worked awesome. They found gamma ray bursts everywhere. And fortunately for world peace and all of humankind, none of them were coming from Earth. They instead found bursts of gamma rays coming from all over the sky. And for years, we had no idea what these could possibly be. It took until the year 1998 before we definitively associated a gamma ray burst with a supernova in another galaxy. This was gamma ray burst 980425 because it happened in 1988 on April 25th. Very creative. And another one of our supernovae with the year and letter names. This association told us that at least some gamma ray bursts were being made by these collapsing massive stars. We now have missions that are specifically designed to look for and alert us to new gamma ray bursts. This is the SWIFT spacecraft. It was launched back in November of 2004, and what it does is not very dissimilar to what the Vela satellites did. It will orbit the Earth and use this large flat region in the front of the telescope, a gamma ray detector, to monitor a huge piece of the sky and look for a flash of gamma radiation. You'll notice that this spacecraft has multiple telescopes on it. It has this big gamma ray telescope here. It also has X-ray and optical telescopes up top, and because we don't want the sun to contaminate X-ray or optical observations, we gave it a little baseball hat to kind of shield those two telescopes from the sun. But you can watch what SWIFT will do when a gamma ray burst happens. It'll be orbiting the Earth, pointed at a large piece of sky, and when a gamma ray burst happens, it'll immediately spin and point at it and localize that burst as best it can, and then send a notification down to Earth saying, a new gamma ray burst has happened, get busy. Get doing whatever you want to do to try and study one of these stars. So all of the stuff that I've been talking about, studying core collapse supernovae or luminous blue variables or gamma ray bursts, any event that happens quickly and then disappears, is a branch of astronomy that we call time domain astronomy. And you can understand why. It deals with events that happen relatively rapidly. It deals with events where time is of the essence, and understanding how they behave with time is a key way of understanding the object. And it sounds like it could be pretty exciting. A new gamma ray burst goes off and everybody goes to work. And something I kind of like to explain is the difference between how maybe Hollywood would depict astronomy and how it works and how it actually works. So in the movie version of time domain astronomy, a new supernova happens and it's, threatening all life on Earth everywhere because it's a movie, and the science siren goes off. Oh my God, we found a new gamma ray burst or supernova, everybody go to work, everybody start observing. Astronomers would look with their eyes, was that me? Yeah. They would look with their eyes through telescopes while wearing lab coats for no apparent reason, either a little telescope in their backyard or an enormous telescope at an observatory somewhere. And of course, they would see something like this. They would see this beautiful, amazing explosion in action, and all the data would be perfect. And they would say, my God, we've discovered a supernova, and we immediately understand everything we're looking at. And they would, call the president and explain what they had found, and Earth would be saved and the movie would end. So time domain astronomy doesn't quite work like this. In the reality, when a gamma ray burst happens, this is usually how we find out. People will get a text message or some kind of notification on their phones. People used to have beepers, now we find out through our iPhones, but you'll get a notification that a new event has happened. At this point, you can call or notify observatories around the world that are set up with what they call target of opportunity observations. You can contact someone like the Keck 10-meter telescopes, this pair of beautiful telescopes on the top of Mauna Kea in Hawaii, and say, we have a new supernova or a new gamma ray burst that we want to observe. Sometimes you're able to interrupt what the observer is doing. Other times you just try to get to the telescope as quickly as possible, which sometimes can take half a year or even a full year, and try to observe the event as it's fading away or right away, however good your timing has been. So this is a really pretty picture of Keck, but I want to put into context just how big they are. That's like a 6-foot-tall guy, and that's just one of the two 10-meter buildings. So when a telescope is this big, you're not, unfortunately, looking through it. I don't even think they've made an eyepiece for Keck. This is what it looks like when you're observing at a telescope like Keck. This is a picture of my workstation from one of my visits to Keck, and you can see all the different things that are going on. We have many computer screens giving mechanical information about the telescope, charts for what I want to observe, a night log where you keep track of every exposure and everything that's happening. You have the data from the telescope itself. It's maybe not quite as pretty as that illustration, by the way. The status of the telescope, where it's pointed, the weather, the notes that you're taking on your own laptop when you're not on the internet. I've got this little to a remote control labeled operator, because this desk is not at the Keck telescopes. It's not even on the mountain. It's down at sea level in a completely different part of that Hawaiian island. And the operator is on a little television screen that I'm talking to via a teleconferencing tool. He's sitting up at the telescope, and I'm down on the ground. And then finally, there's a very important observing tool, my Kindle, because while you hope that every single observing night looks like this, occasionally you get nights that look like this. This is a real picture that I took. That is the view from this telescope to this one. And when you can't see the gazillion-story building right next to you, your odds of looking at a supernova that's hundreds of millions of light years away are not good. And if that happens, that's how your night goes. If you've been given a night on a telescope and it's cloudy, that's all that happens. You don't get to reschedule for the next night. Someone else is coming in to do their own science. You sometimes have to wait an entire year until that object is back at the same place in the sky to do this again. So this is just part of the cost of doing business as an astronomer. This goes away with something like Hubble. Hubble is, for the most part, immune to the sorts of weather problems that we have here on Earth. And I actually have had people ask me this. No, we do not get to go to Hubble to observe. I would be first in line if we could, but Hubble will actually take instructions from someone who wants to observe on it very far ahead of time. You'll line up all the information you need for how exactly to point at what you want, how exactly you want to observe something, for how long, with what instruments, in what wavelength, whether you want to take a picture or a spectrum. You give it all that information ahead of time. Hubble will take the observation, and then you'll wake up and you'll have an email saying, Hubble observed astronomy for you last night. Here is all of your data when you want to go get it. So it's maybe not as interactive as sitting at the telescope, but the data that you get from it, as you've seen from all the images, is beautiful. It becomes beautiful, but it's not really how it looks when you first get data. This is what actual data straight off a telescope looks like. It's pretty gross. And maybe the object that you're interested in is not the really bright thing that's very obvious. Maybe it's this little blip over in the corner. So there's a lot of work that needs to be done on the image before you can understand what you're looking at. And finally, once you're done, you do not at least so far, get to call the president with what you found. You mostly want to tell other astronomers, and you'll do that through a variety of different websites or publications. We have the Gamma Ray Burst Circulars Network. You can see that it's talking about a gamma ray, this is a shot from today, talking about a gamma ray burst that happened just a few days ago on May 30th of 2015. This will constantly update with new gamma ray bursts that we found. You have the Astronomer's Telegram website. I love a website that's named after a telegram that will give you updates on new supernovae. We can publish our results in things like the Astrophysical Journal, the monthly notices of the Royal Astronomical Society, places where we can write papers and get other astronomers to read them. So this is, for the most part, how we announce when we've found something new and interesting. And this is the reality of how time domain astronomy will usually work. There is one exception. So you remember this depiction from a while ago of the supernova that happened in our own Milky Way, 6,500 light years away, that was so bright you could see it during the day for 2 weeks. We have a pretty rough estimate of how often a star should explode in our galaxy. We can figure out roughly how fast the galaxy is making new stars. We can guess how fast those stars should be dying, and we can figure out roughly how often something like this should be happening. And as far as we understand it, we are overdue for an event like this. So what I love imagining is what would actually happen if tonight or tomorrow a massive star exploded somewhere in the Milky Way and we saw this from Earth. It would maybe be a little bit alarming at first, something getting brighter and brighter and we don't quite know what it is. Staying visible in the daytime sky for weeks would be incredible. You would be able to see the sun and this one other thing in the sky for that period of time. It would be fascinating. We would have numbers and numbers of news reports on it. The supernova would get a hashtag. People would be Instagramming their pictures of it. Jon Stewart would be talking about it on The Daily Show. And trust me, every time domain astronomer would collectively lose their minds with excitement. This would be unbelievably cool. And it's fun to think about how exciting it would be if a galactic supernova actually did happen sometime in the near future. Nope, we don't think so. We're still here after the 1054 supernova.
Is it the government organization? It's a joke.
Well, there are, no. There are debates about what would happen if a gamma ray burst went off too close, and we happened to be right in the beam of the gamma ray burst that was right near us. And we don't really know what might happen. It could be not that good, it could be fine. Since it's traveling at the speed of light, we get no warning before it gets here, so don't worry about it. Nothing we can do. So I've talked about how massive stars explode. I've talked about how they evolve. I've talked about supernovae, and I've talked about what they leave behind. And we've definitely listed off a bunch of incredibly weird stars. Something like a red supergiant, undeniably weird. Something like a neutron star, also undeniably weird. About the only thing that could make stars like this stranger is if we tried combining them. So to explain what this is, I need to go back to the research that I was doing on red supergiants about 10 years ago. I started doing this work in 2004 and kept working on it for years. And like I said, we weren't calling the president with our results, but we were writing papers and sending them out to the community. And one day in the midst of doing this work, my collaborators and I got a really interesting email. And the email started out, years ago, Kip Thorne and myself invented theoretical models of stars, went on to describe these stars, and then asked if we would be interested in looking for them. And this was an email from a woman named Anna Zhitkov in the UK. This described a completely new type of star that she thought we might be interested in looking for. And these are called Thorne-Zhitkov objects after Kip and Anna. They predicted these stars back in the 1970s. What they predicted was a star with a neutron star for a core, that tiny little quantum physics-supported star, surrounded by a big, cold, puffy envelope that from the outside would make it look like a normal star. So they call these theoretical stars because they were a great idea. All the math worked out saying that a star like this should exist, but we'd never ever seen one. They sound bizarre, but we actually know a couple of ways that you could maybe make a Thorne-Zhitkov object. We think that Thorne-Zhitkov objects, we'll call them TZOs for brevity, come from a binary star system. So this would be two stars in orbit around one another, gravitationally bound, and going through their evolution together, perhaps even influencing each other's evolution. There's two different ways that we think a binary star system could make a TZO. The first is what we call the engulfing scenario. In this scenario, you have a blue supergiant, something on the main sequence, hot star burning hydrogen, and a neutron star as its binary companion. Now, when that blue supergiant moves from burning hydrogen to burning helium, it will start to expand and grow, and it will eventually swallow its companion neutron star. That neutron star will go spiraling into the center of the red supergiant, and that's one way to make a TZO. Another way is what I call the collision scenario. In this case, you have a red supergiant and a higher mass companion. So the more massive a star is, the shorter its lifetime is, so the more massive star will go supernova first. That massive star will go supernova and make a neutron star. So when we do the little illustrations of supernovae, we typically imagine the whole star just going and doing this. In reality, they're never perfectly symmetrical. You'll always have a little bit of asymmetry somewhere in the explosion, and what it'll do is kick the neutron star in a particular direction. So in this scenario, you have a red supergiant, a star that goes supernova, it will make a neutron star, and that neutron star will go flying off in a particular direction. Sometimes it will go flying directly into its companion. I love this scenario because it imagines that the supernova has a really awesome aim and just kicks a neutron star straight into the companion. But either way, it's another way of putting a neutron star inside a red supergiant and making a TZO. So these sound like really interesting objects, and they sound like something that we should really be looking for, but this is the difficulty. That little animation that I showed you kind of lied, and you know it lied. A red supergiant is the size of Jupiter's orbit. A neutron star is the size of the city of Baltimore. So when you actually combine them, it's going to look like this. A Thorne-Zhitkov object is, from the outside, going to look exactly like a red supergiant. So searching for one is going to be incredibly difficult. But it's not quite impossible. They look almost exactly like red supergiants. And to understand why, we can use my little, very high-tech PowerPoint drawing of what a cross-section of a red supergiant is to look at the difference of what's going on inside these stars. This is the cross-section of a red supergiant. You have the star's surface, you have that core that's burning helium, and in the middle you have what we call the star's envelope. And this envelope is experiencing convection. It's sort of stirring up the star to a certain degree. Maybe part of the envelope will be getting stirred. In a Thorne-Zhitkov object, this is a little bit different. You have the surface of the star, you have the neutron star core, but that entire envelope is getting stirred and mixed up, and things are moving around inside the star very, very fast. So what you can imagine is a packet of material in that star that is very, very rapidly moving around. It will get dragged down to the very base of the envelope, and down here it's very, very hot, and the pressure is very, very extreme. You're right near that neutron star core. When material is down there, it will get bombarded by protons. Protons will be getting forced onto the nuclei of the atoms in that little packet of material. There's only so far that you can go with that before you reach a theoretical limit of what you can do to those atoms. But before we hit that limit, that packet gets dragged back out into the exterior region of the TZO. When it's out there, it's not getting bombarded by protons. Instead, it will emit electrons or positrons or neutrinos. This will happen over and over and over. And what ultimately happens is that the results of that repeat of being bombarded by protons and then decaying and then doing it again over and over very, very fast, the results of all of that get dragged to the surface of the star. And what you wind up with are all these strange elements sitting on the surface of a Thorne-Zhitkov object. Things like molybdenum or lithium or rubidium. Maybe not the most popular elements in the periodic table. You don't necessarily hear as much about them as you hear about hydrogen or helium or oxygen. But they're very interesting elements when we try to understand how the universe works and how we make new elements. They're also really not expected to be found in any significant quantity in a normal red supergiant atmosphere. So what we can do is look at red supergiants very, very closely. We can see if any of those red supergiants are actually hiding TZOs that have extra amounts of molybdenum, lithium, and rubidium in their atmospheres. And that's exactly what we did after we got Anna Zhitkov's email. We had observed a bunch of red supergiants in the Milky Way and in a couple neighboring galaxies, and we went back and observed them again. We used the 3.5-meter telescope at Apache Point in New Mexico to observe stars in the north. We used the 6.5-meter Clay Magellan telescope at Las Campanas in Chile to observe the stars in the south. And the reason we were repeating our observations is because our data before looked like this. I showed you this before, red supergiant spectrum. We have color going from blue to red on the horizontal axis and brightness on the vertical axis. This was what our old data looked like, but we needed way more detail. We needed to be able to zoom in on very specific pieces of the spectrum and look for tiny little individual bumps and wiggles and little individual places where light had been absorbed from something like molybdenum. And that was what we found. We found a little tiny bit of molybdenum being absorbed in a normal red supergiant. We found light being absorbed by lithium, and we found light being absorbed by rubidium. This in itself was already pretty cool. Nobody had ever checked to see how much normal red supergiants had molybdenum. So we did this for all of the red supergiants that we reobserved, and every single one looked just like this. We saw these little blips of absorption shown in red that showed us those elements were there. Every single one looked like this except for one. This was what one of the stars looked like, and I've made everybody go, ooh, and this doesn't get that kind of reaction, does it? I can compare them again, and you can see how all the red lines get a little bit stronger. But this is another explanation of how actual science works. You don't look at something like that and go, Eureka, we've discovered something amazing, the planet is saved. You look at it and you go, that's weird. And that's actually the best sound that you can hear in science, is it's not, Eureka, we've done it, it's, huh. And that was what we said when we saw this star. It turns out that it has an excess of molybdenum, it has an excess of lithium, and it has an excess of rubidium. It has everything that you would expect chemically in a Thorne-Zhitkov object. We had found the first observational candidate for confirming that stars like this actually exist. So this was really exciting. And the idea of discovering a Thorne-Zhitkov object is mind-blowing when you think about it. The existence of a TZO would have enormous implications for almost everything that we study about stars. Remember, this is a completely new model for how a star can work. Every luminous star that we have seen like this before is burning something in its core. These stars aren't. They have neutron stars in their cores. They give us a completely new fate for any massive star in a binary system. It tells us how a binary system can ultimately end its life and perhaps hide as a single star, even though there's one star hidden inside another. They also give us a totally new way of making elements. You hear Neil Tyson on Cosmos, or you hear Carl Sagan on Cosmos, talking about how we're all made of star stuff, and how every element that we know about was at some point made in a star. This gives us a new way of making some of those elements. An element like lithium is a really strange and interesting puzzle piece for how we understand the very early universe when we were just starting to make elements. So having a totally new way to produce lithium is really, really interesting. So discovering a Thorne-Zhitkov object would be amazing. And that's exactly why, if you remember, I called this a candidate. And the reason why is something that I think gets referred to as the Sagan standard. It's this idea that extraordinary claims require extraordinary evidence. Discovering a Thorne-Zhitkov object would be an extraordinary claim. Our evidence is 3 little red blips. It's very good evidence. It's been very carefully observed and very carefully analyzed. We think that it really might be a TZO, but it's not enough. There's a lot more observing that we need to do. There's new computer models that we want to run for how stars like this might look. These really would be the weirdest stars in the universe. And if we want to know for sure that we found one, there's a lot of science that still needs to be done on the star that we found and on others like it. So on that note, I will go back to my opening slide, and I'm happy to answer any questions that any of you might have about weird stars. Thank you very much.
Thank you. That was wonderful. Thorne-Zitkov objects take us to a place that we had never really experienced before.
Yeah.
That's a great thing to finish on. All right, so questions.
Yes.
Just to give an idea of scale, the Crab Nebula, can you tell me approximately what the distance is from one side of that nebula to the other?
I do not know. I would have to look it up.
I
It absolutely
believe it's
dwarfs.
an order
the-
of 14
yeah.
light years across.
14 light
On
years?
order, something like that. That's coming out of an old brain that doesn't quite remember everything as well as it used to.
Keep in mind, it's also growing. That only got made less than 1,000 years ago, so that material is still slowly expanding and puffing out, so it'll keep getting bigger.
Thanks.
Yeah. Yes.
What's the next step to find a TZ to make the candidate more acceptable?
It's a great question. And so I worked on this project with several other astronomers. I actually worked on it with Phil Massey, the same person that I did my first research project with. I worked with Anna Zitkov and with an astronomer in Chile named Nydia Morel. And all of us are now kind of investigating our own ways to confirm or refute that that's a Thorne-Zitkov object. I know that Anna is working on getting more observations of other stars like it to see if we can find others. Something that I'm really interested in doing is working with computer modelers. We haven't really modeled what a Thorne-Zitkov object should look like in about 20 years, and computers have evolved a lot. So we're hoping that we can get new predictions for what else we might see. We're hoping that maybe they'll predict that it'll emit X-ray light, or that there will be a magnetic field that we can see some signature of. We really don't know. But as we get more predictions, then we can turn around and say, point Hubble at it, point Keck at it, point whatever we need. But I'm waiting to see what we learn with new computer models about how they should really look.
And I think that emphasizes one of the sea changes in astronomy, in that you can work from computer models to observations, ground-based observations to space-based observations. The number of avenues you have for exploring these problems really has grown.
Yeah.
You're at a great time in astronomy.
They feed back and forth on each other too. When we moved those red supergiants and we changed their temperatures, people doing new models of stellar evolution used what we'd observed as a sort of benchmark to make sure that new models agreed with what we'd seen. So it goes back and forth all the time.
Because usually observers would look at those computer models and say they don't match observations. Well, obviously the computer models are wrong.
And that's what we did for a long time. We said, oh, it's wrong, blame the computer people. And then they kind of came back saying, no, you really need to check what you're observing too. I saw that you had a question. I'm sorry, there's someone behind you. He's had his hand up since the beginning.
Antares or Betelgeuse ready to go off anytime now? Are they full size?
We don't yet have a good diagnostic for when a star is about to explode. There is a paper that was written that in its abstract says, Betelgeuse clearly is about to explode. It could go off any day now. It could be really incredible. And I think the paper is from 1954. And we would love to be able to do this. This is actually one of the sort of eventual goals of time domain astronomy, is being able to look at a star and say, that is going to explode in 10,000 years or 10 days, and it's going to look like this. And right now, all we can kind of do is study supernovae, maybe look at old images to see if we can find what the star was before it exploded and piece it together from there. But we would love to be able to predict when a star will explode.
So, but wait a minute, if 2009 has actually gone off,
Yes.
does that show us that there is a trigger with these LB luminous blue variables?
Yes.
That shows us
would
that,
be
you know,
the best studied supernova that we know about, because we have images and we have spectra and we have all sorts of data on the star from before it exploded. We type supernovae according to the elements that we see in the supernova spectrum. We have one specific type of supernova, it's called a 2P for reasons that are not worth getting into, that we think come from red supergiants. When we look at the galaxies where those supernovae exploded before the supernova happened, we can sometimes find a red supergiant at the supernova position that's gone when we go and look again. So we know that red supergiants make those. We now think that LBVs make another type of supernova called a 2N. Those are two of a bunch of different types of supernovae, and for most of them we still don't know what the progenitor star is, but 09IP is the best example.
yeah,
that
and if
we have.
09IP could tell us when Eta Car is going to go off, that would be really cool.
That would be really cool.
In the back
Yeah.
there.
Oh, sorry, there was a question right here that
Oh, sorry.
had his hand up, and then yeah.
You, in the diagram, you're showing that there is a loop process at work. Would you be able to observe over time an increase in the amount of lithium that would be showing up in the spectroscopic analysis? And if that happened, wouldn't that be confirming of the process?
In theory, we could. What we don't know is how long that process takes. This was actually a paper written about 10 years ago by somebody that was specifically talking about lithium enhancement in Thorne-Jitkov objects. We don't think that it'll increase fast enough that we can watch it, but if we ever hit a point where we have spectra of hundreds of Thorne-Jitkov objects, the amount of lithium might be an indicator of how old it is. That if it's relatively new, it maybe won't have a whole lot of lithium at the surface yet, and then as it ages, we'll see other lithium and other elements get progressively enhanced. But we can't do that with one object. We really want to hopefully find a bunch, and then maybe that would be a way to test age.
When you describe solar core processes, you use the term burning. Is that like shorthand for?
It's shorthand for nuclear fusion. It's shorthand for nuclear fusion processes.
And it's essentially driven by gravity as the energy source that
It's
fuse those together.
It's not quite gravity as the energy source. What's happening is, as a result of gravity, the temperature and the pressure conditions build up to a point where nuclear fusion gets ignited. You've probably heard in other talks about brown dwarfs, which are these tiny little stars that are much, much, much smaller than the sun. They're a fraction of the mass. Brown dwarfs actually do not get hot enough in their cores to burn hydrogen, because in part they're so tiny and the temperature and pressure never get extreme enough. Some people call them failed stars because of this, which is kind of a depressing term. They're just different stars. You could do a whole other weird stars discussion on tiny stars, but that's sort of the opposite of what's happening in stars like this, where you actually do build up the conditions to the point where hydrogen fusion and then later helium fusion kicks off.
Right. We sometimes refer to stars as gravitationally confined nuclear fusion reactors.
Yeah.
So the gravity is not the proximate cause, but it is one of the contributing factors. Other questions?
Question on the supernova that could be nearby that you say most astronomers would be excited about. Is there a possibility that a close supernova could adversely affect circadian rhythms, cycles on Earth for extended periods of time, eliminating nighttime?
Yeah. I've given this talk a bunch of times and I've never gotten that question, and it's fascinating. It could. It's interesting to wonder what it would do. I don't know that it would impact human circadian rhythms. It would still get much darker at night. We don't think that it would be as luminous as the sun. It would more be like having a second moon, probably. But it's interesting to think about what it would do to other animals that are more sensitive to changes in light. Like, I have no idea what it would do to an animal with really solid night vision, or animals, for example, that see in polarized light. Something like bees actually see polarized light, and I don't know what the light from people study the polarization of light from supernovae, and maybe it'll really mess with the bees, I don't know. But that's a really interesting question.
And it's intriguing because we know how the animals react when we have solar eclipses. And that if you've ever experienced, one of the cool things about experiencing a solar eclipse, and by the way, August 2017, put it on your calendar, total solar eclipse coming straight across the United States. You must see it. It's the best one in your lifetime, okay? We know how animals react as it just starts to feel like dusk is setting you know, even though the sun is high in the sky. So the opposite of adding extra light.
You imagine there would be stress animals that sleep when it's dark, and really well-rest animals that don't. But that's a super interesting question.
Other questions? All right, if not, we will see you next month, Tuesday, July 7th, if I've got it right. 4, 5, 6, that it should be Tuesday, July 7th. Let us give Emily a thank you one more time.